Hello everybody, we're going to talk about problem 93, one of my favorites. I love it because it has this outlier and it talks about what we have to do with it. So, the first thing they ask us in 93 is, this is the problem about a baseball and a softball, figuring out which one you can throw further. They went out to 24 students and they had them warm up and throw each one as far as they could, and they looked at the difference. And the key thing is they went up to 24 randomly selected students. The fact they went to 24 randomly selected students and not 24 students and asked them to throw a baseball, and then 24 different independently selected and sampled random students and asked them to throw a softball. They didn't do that. They went to 24 students and said, hey, please throw a softball and throw a baseball. They went to one sample. And then they went to that one sample and they compared the two. And if they're comparing the two, the baseball and the softball, within each individual person selected in the sample, what we have is paired data. So I'm going to write the answer to 93A, but I just want you to hear that first from me, right? Why? Why is it, right? Why is it paired data? Well, the reason why is because it's not one sample and looking at the differences in each person selected. They're asking, look at their individual differences, and that's what they're measuring. So I'll write this out for you in a second. So this would be my response to A. One sample was chosen, then two variables were measured for each student in the sample. When you see two variables for each student in the sample, classic paired data. It's definitely not two independent samples. So the next question they say is, they created a box plot, and the box plot has a clear outlier. And the fact is, the mean, look at the box plot, right? It's way above 0. So you look at this, I mean, most of this data is positive, right? Most of the data points are positive. So therefore, if most of the data are positive, we have far higher likelihood that the baseball can be thrown further than the softball. We also have this outlier, which is concerning, but the fact of the matter is I want you to see the fact that most of the data, right, most of the data are above 0. And if most of the data are above 0, that means the baseball minus the softball is probably positive, right? So therefore, most of the time, baseball can be thrown further than a softball. Now, in this problem, it's clear that the box plot, most of the data points are above 0, and even the 25th, the first quartile, the 25th percentile, even that's above 0. So it's pretty clear. Sometimes you can't be quite as definitive as my statement here, but because it's pretty clear that most of the data points are positive, and at least 75% of them are positive, therefore it's pretty easy to conclude that most students can throw a baseball further than a softball. And that's true for this data and not for all data. So our hypothesis, we have to basically ask, what's the question that we're asking? And a key thing is that we're talking about paired data. So we're going to be talking about this difference, right? We're talking about the mean difference here. That's the main question that we're asking. We're not talking about two different samples. We're looking at this mean difference, and that's all we're going to care about. So we know that our null hypothesis equals 0. And the question is, what are we going to have here? Is it less than 0? Is it greater than 0? Is it not equal? I mean, it's tempting just to come and say, well, is there a difference or not? Well, that'd be, is there a difference? But in order for us to actually determine what goes here, whether it's one-sided or two-sided, and what side it is, we have to go read the initial question. What are they asking? So I'm going back to the book, and I'm reading the first part. Have a ball. Can students throw a baseball further than a softball? What does that mean? Well, can the baseball be further? We want to know, is the baseball distance greater than a softball distance? Well, we want to know. We're trying to prove, right? We're trying to prove that. That's something we're trying to actually discover. So we're going to use a greater than symbol. Okay? Now it's tempting, ready? And I just made a big mistake, right? I just moved on to part D without doing the most important thing for hypotheses. You cannot move on to the next section unless you define those variables. We need to define this clear as day. So where U difference is what? Well, this is the true, because this is the true mean, the true difference. I always like using true difference because it kind of gets the fact that we're talking about a parameter here. The true difference, person can throw a baseball and a softball. So this is like the true distance. If we can have everybody in the world throw a baseball and a softball, the true difference would be this. And it's good to kind of clearly define that we're talking about baseball minus softball, just so people know what direction it's in. So it was nice to have that as well. Yeah, from the 1 to D. Explain why the normal large sample condition is not met. Well, first of all, 24 is less than 30. And usually that's not a big deal, right? 24 is less than 30, no big deal. So the central limit theorem doesn't work. And usually you just go back and say, well, as long as we have no significant skew and we have no outliers, we're fine, right? We go up here and we say, uh-oh, right? That's a problem. That's a pretty big outlier. That's actually a huge outlier. So the outlier means that the apparent population, right, the population of all differences, might not be normal. It could be bimodal. It could be something where there's a significant skew. We just happen to see one outlier, but maybe there's a weird skew. So we don't really know what the parent population is, but that outlier means that the parent population may not be normal. And if it's not normal, and we haven't gone out to at least 30 people, then we have a problem. So what are we going to do? Well, we actually can't do any of our normal inference because we can't use the normal model or the T model. We can't go out and do TCDF if we don't have some kind of reliance upon the fact that it's normal enough. Now, if you're asked to do this on a test and you had that outlier and they didn't prompt you with all these possible questions, you should still do the significance test, folks. Proceed with caution, say, hey, this is not something we should really count on. This isn't a result we should use. But if you were asked to do this, you should still proceed with caution. But in this scenario, they're not asking you to proceed. What they're asking you to do instead is to use some, quote unquote, imitation of a sampling distribution. So what they did is they said, we're going to go out and do a simulation, and they're going to do 100 trials of a simulation, and they're going to basically say that if the mean difference in distance was 6.54 yards, right? How likely is it that you would get 6.54 of a mean or greater if the null was actually true? So what they did is they performed the simulation and they tracked the differences in this distribution. And if you look at it, you see there's I think 100 of those little dots. Yeah, results of 100 trials of the simulation. There's 100 little dots there. And now let's see, what's the likelihood that we get 6.4? Well, I can't tell exactly, but to me, it looks like it's maybe never. Maybe that one out there is a 6.54, but it might be none. It looks like either one or none of the 100 simulations has a difference of 6.54 or more. I mean, that one dot on the far outside. I don't want to draw up the whole dot plot for you folks, but if you look on page 689, you'll see on the far right there's this one point that it could be 6.54. But therefore, if you did all these simulations, how many of them, right? How many of them? Well, I guess the p-value, I really wish I had the exact value there. So I just took a second to take a closer look, and if I used kind of a ruler, it's pretty definitively 0 out of 100. That far point, that point on the far right, that's right of 5, is likely to be less than 6. Even if you call it 6, it's definitely less than 6.54. So therefore, from the simulation that they did, they basically say, hey, let's do a whole bunch of simulations, assuming that they're both true, that the null is true, and both the difference is 0. So really, either one could have been greater, right? The softball might have been the bigger one. The baseball might have been the greater one. So they went out and they did a simulation of this, and then they averaged them all. And in 0 of the 100, 0 of the 100 had a greater than 6.5. So 0 of the 100, so I'm going to get this, of the simulation, of the 100 simulations, had a score or a mean greater than 6.54. So the p-value is effectively 0. And therefore, what do we conclude? Well, that's pretty convincing evidence that the baseball in general can be thrown further than the softball. So I'll conclude that and write that out for you. So we can conclude that we've convincing evidence that the baseball can be thrown further, that on average, I mean, that on average, the baseball can be thrown further than a softball. right? I mean, on one given day, a person can go out and maybe throw a softball further, but on average, the baseball can be thrown further than a softball. And this is only possible because they did the simulation and they went out and did this kind of, hey, let's assume that either one can be thrown further, and let's do a simulation and have basically a sampling distribution. It's not an actual sampling distribution, but it's a kind of imitation or a partial sampling distribution. Using that partial sampling distribution, which is that dot plot on page 689, we can then surmise that, yeah, this is getting 6.54 of a difference is a pretty big deal. It's therefore very, very, very unlikely that you're going to have a difference of 0. It's much more likely the baseball can, on average, be thrown further than the softball.